Hi friends, a very good evening. Could you please confirm in the chat window if you are able to see my screen and if you can hear my voice? I have the chat window on a different computer so that I can see it clearly. Can you please confirm that so that we can start the session? And I also have a few quick updates. I know some of you are asking about the changes in videos and stuff like that. I'll update you before we dive into the interactive problem solving itself. So first, can you please confirm in the chat window if you can hear my voice and if you can see my, if you can see my screen being shared. Cool. Thank you, folks. Thank you. Thank you for confirmation that everything is sounding all right and looking good. So, hey, folks. So it's already 7 p.m. So let's dive into the discussion. Some of you have questions about these top MSQs and stuff like that. I'll just cover them in a couple of minutes before we dive into the session. First and foremost, this is the third interactive problem solving session for operating systems. With this, we will complete operating systems. The next 3 sessions will be on the 14th, 19th and 21st, and we will cover computer organization and architecture. Right? So just wanted to give you that heads up so that you're prepared for the next 3 interactive problem solving sessions also. All these 3 also will be publicly available. Next, okay. So quick updates. Let's go one by one. So as far as GATE 2021 itself is concerned, we have put a couple of videos, one detailed video and one short summary on our YouTube channel. Please check them. We've also shared detailed notes on all the concepts, every nitty-gritty thing that has been changed. Thankfully, a lot of topics have already been covered. Some of you in the chat window are asking about compiler design. We already covered some of the concepts from code optimization because they were earlier there in the GATE syllabus. The remaining parts, I think we would require another 30 to 45 minutes of videos. We are already preparing the notes. We will update both our PDF version of the notes and the videos as soon as possible, right? So we will do it very quickly. Okay, we'll do it quite fast. I think from the videos, addition of new concept videos, I think general aptitude will take most time because that has the most number of topics. Rest of the subjects, just few topics, so we'll do it fairly quickly. For example, compiler design, we'll do it very quickly. Operating systems, we already covered system calls, but we'll quickly do it. Discrete maths, monoids are already been covered. So most of the concepts have been covered. Compiler design, we might require about 35 to 45 minutes of videos for the topics that are missing. We'll do that quickly. Operating systems, so these are very simple. I think general aptitude, because the syllabus has increased substantially, will take us more time. Number 1. Number 2 is some concepts have been removed. For example, in computer networks, right? The network security part has been removed. Similarly, IPv6, so network security, IPv6, I think wireless LAN is also removed if I'm not wrong. Again, we have a YouTube video where we discuss all these details. So all these topics will be moved into a section called as optional videos, right? So we will mark it optional videos so that you can skip those videos for GATE 2021 preparation. That's a very important thing, right? So next thing is, as far as MSQs are concerned, we will be adding MSQs in the test series itself, right? So in test series, we are modifying some questions to convert them into MSQs. As I've mentioned in the detailed analysis video on our YouTube channel, we have done a lot of analysis on the JAM examination that is conducted by IITs and IISc for research roles. And their MSQs are typically fairly easy, but they're slightly tricky to trick you to making silly mistakes. And also these interactive problem solving sessions will be adding MSQs. Again, we have just started doing it. We modified a couple of questions that we initially created to make them MSQs, but we'll make more interesting MSQs as we go forward in the interactive problem solving sessions. For example, in today's session, I think we have 2 problems which are MSQs, right? So those are some of the quick updates. Again, I've also answered, I think our team, our mentors have also joined, and they've also are also answering some of the questions there, right? So those are the quick updates, right? So anything that you have questions on, feel free to reach out to us. You can just go to gate.appliedcourse.com. So you can just go to gate.appliedcourse.com. You can reach out to us on this phone number or email us. We'll try to respond as soon as possible, right? So anything that I could not cover here, okay? Since we have 10 questions and we want to finish operating system third part, let's dive into the questions. Again, This part of the operating system is very, very easy if you don't make silly mistakes. Okay, here is the first question. Let's tackle these questions. Again, let's focus on solving these problems because that's what matters. The small changes that you have in the GATE syllabus will not make a big impact if you have been seriously preparing and if you continue to seriously prepare. These are minor changes. They will not impact your GATE preparation significantly. So let's get back to the preparation. Let's get back to problem solving and let's start solving the operating systems concepts, right? I'm happy that our team is also answering some of the questions here. Cool. So again, I'm looking at the answers in the chat window. So please put your answers in the chat window. Once enough students have answered, I'll answer the question, right? So let's go into it. Okay, here comes the first question. Very simple question. It's a very simple, basic question. Again, you sometimes get these easy questions in GATE. So you will have some few medium problems also here, but some of them are easy. Yeah, cool. Most of you wrote it. The answer is C. It's a very simple thing. Again, from these sections of operating system, you typically get fairly easy questions, by the way. So we know what thrashing is, right? Thrashing basically happens if you're using a virtual memory scheme. And when lot of time, look at this, a process is thrashing if it spends a lot of time paging rather than executing on the CPU. Right? That's what is thrashing. Again, you might have seen this diagram in most textbooks, right? If you have number of processes here and if you have CPU utilization here, right, or effective CPU utilization, as the number of processes increase, the CPU utilization increases, but at some point it will fall sharply and this region is called thrashing, right? This is a very common diagram that you may have seen. And this occurs because most of your processes are spending time performing the paging rather than executing and utilizing the CPU. Trivial question, very easy question, right? So let's go to the next question. Again, we'll start with some easy questions and most of you got it right, which is very good. So let's go to the second question. This is also fairly easy. If you know the basic method. 1 second, I think I messed it up. No, okay, so this is all right. Okay, this is the second question. Okay, this is the second question. Again, folks, some of you are asking slightly open-ended questions. It's hard to answer them in the chat window while our mentors will try to answer them. You're most welcome to reach out to us. Just go to gate.appliedcourse.com, reach out to us over email. We'll try to answer as many questions as possible. Of course, we give first priority to students who are enrolled in our course and our test series. Okay, just think about it. This is a good question. It might be slightly lengthy, but please be careful, you'll get it. I see a few people putting in your answers. Just be careful and avoid silly mistakes. Again, most medium level questions in GATE are easy, but they are prone to silly mistakes. Again, as our mentors are also saying in the chat window, please focus on solving the problems. Any questions you have, feel free to reach out to us over email. We are there to help you. We answer hundreds of general queries from students like you. Even students who are not course enrolled, we answer because we want everybody to succeed in this process. So let's focus on problem solving now. Okay, I see a bunch of you putting in your answers. Okay. This is slightly lengthy, but if you're careful, it's very easy. Again, most of you got it right. The answer here is 10. Again, these are the typical type of problems that you encounter in GATE. As I just mentioned, most of the problems from these sections of operating systems are very, very easy if you know the concept. Again, I think one or two of you got it wrong. So let's actually see it. So we've drawn this diagram here just so that it's easier for us to show it to you, right? So this is the sequence of page numbers and we are using LRU, right? So initially these are the 4 frames that we have. frame 1, sorry, you have 1 here. So all of them are empty, so you place 1, right? Here there is a page fault happening because all the 4 frames are initially empty, right? So you're asking for this 1, so you fill it, so there is a page fault happening. Then you ask for 2, there is a page fault that happens. So whenever there is a page fault, we are listing it as page fault here. Then 3, the third page fault. 4, the fourth page fault. Cool. Now comes 2. 2 is already there in our 4 frames, so no page fault here, right? Then you have 1. 1 is already there. Look at this. 2, there is no page fault. 1, there is no page fault because 1 is already there in our 4 frames, right? Then you get 5. When you get 5, you realize that 5 is not there in any of the 4 frames. So you need to replace one of them. And the replacement strategy is LRU, right? So if you notice, what is the least recently used? So the most recently used is 1, then 2, then 4. The least recently used is 3. So 3 gets evicted or 3 gets thrown out and 5 gets put here, right? So 3 gets evicted and 4 gets put in here. Sorry, 3 gets evicted and 5 gets put in. And there's a page fault that happened here, right? Then next thing you get is 6. Again, 6 is not there anywhere. So which is the least recently used? Look at this. 5 is the most recently used. 1, 2, 4. 4 is the least recently used. So 4 gets evicted and 6 gets placed here. Look at this. 4 gets evicted and 6 gets placed. But there is a page fault here. Next you have 2, right? 2 is already there in our frame, so no page fault. 1 is already there. Then you have 2, no page fault. Then you have 3. 3 is not there anywhere here, right? 3 is not there in the 4 frames. So which one will you evict now? Look at this. 2 was most recently used, 1 was used, 2 was used, 6 was used, 5 was the least recently used. So 5 gets evicted and 3 gets placed, and there is a page fault because you are removing 5 and you're placing 3 here. Then you have 7. 7 is also not there, right? Then again you apply least recently used, right? So if you apply the least recently used, 3 is most recently used, 2, 1, 6 is the least recently used. So 6 gets evicted and 7 gets placed here. Then you have another call for 6 here. Again, we're just going step by step here. Let's make a note of all the faults that happen. When you have 6 here, look at this. When you have 6 here, 6 is not there. So you'll again apply LRU. Which is the least recently used? 1. Just keep going back and see which is the least recently used. 1. So 1 gets evicted, 6 gets placed, and there is a page fault. 3 is already there, so no page fault. 2 is already there, so no page fault. Then 1. When you have 1, there is a page fault that happens because 1 is nowhere to be found here. Now, what will 1 get replaced with? 7 is the least recently used. Look at this. 6321 were more recently used. 632 were more recently used. 7 was the least recently used. So 7 gets evicted and 1 gets placed. There is a page fault here. Then 236, all of them are there. How many page faults? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's it. So if you know the LRU policy and if you're careful to avoid silly mistakes, you can easily get the answer of 10. This question could be slightly time taking, but it's very easy to answer if you're careful with it, right? That's what is important. Okay. So let's go to the third question now. Again, we have pre-drawn this diagram so that it's easier for us to answer it and show it to you graphically. Okay, let's go to the third question now. This is an MSQ, by the way. This is an MSQ. We have just started setting, we have modified some existing questions to MSQs right now, but we'll be setting more interesting MSQs in the coming interactive sessions. So we believe that MSQs will be clearly stated that they are MSQs in the actual examination, so that you know that multiple options can be correct and that there is no negative marking and there is no partial awarding of marks. Okay. Yeah, somebody is saying there is a lot of overlap between COA and OS. Yes, there is some overlap between COA, OS, DLD. There are a lot of overlaps in computer science. There are a lot of overlaps between discrete mathematics, digital logic design, because of Boolean algebra. So there are a lot of overlaps there. Please read the question very, very carefully. Please read the question carefully. Because MSQs are simple, but very easy to make silly mistakes on. It's an MSQ, so no partial, if you only get a subset of answers or options correct, you will not get any marks. So please be careful with that. Very simple concept, but very easy to make silly mistakes on. I see a lot of people making silly mistakes. That's expected. MSQs are, somebody was asking how MSQs will impact the examination. It will basically create an environment where more people will make more silly mistakes. So people who make silly mistakes will lose because of MSQs. But if you're careful, MSQs are easy often. I see a lot of people doing silly mistakes even for a very simple problem like this. So please be careful with MSQs. So Rajesh has a suggestion to create a general Q&A session. We'll surely do that, Rajesh. We were also thinking of it. We'll do it for sure. Okay, so some of you have answered it. So let's go step by step. So when you have an MSQ, you have to go through each of the options. You can't just avoid anything here. Okay. So consider the following segment table. You have segment 0 to 4. This is the base address and this is the length of the segment. If the logical address is given by segment number, comma, offset, which of the logical addresses are invalid? Not valid, invalid. Let's look at the first option now. It says segment 1. Okay. This is valid because segment 1 exists. And it says the offset is 20. Offset 20 doesn't make sense because the length here itself is 14. Right? The length of this segment itself is 14. Then offset 20 doesn't make sense because 20 is greater than 14. So obviously this is an invalid logical address. Because it is invalid, this is one of the options. Right? Again, which of the options are invalid or which of the logical addresses are invalid is the question. Next, let's look at the second part, B, 3, 450. So segment 3 exists. 450 is the offset and this has length of 580, which means 450 is less than 580. So this is a valid address. Because this is a valid address, this is not invalid. Hence, you should not tick this. Okay, look at this. It says which of the logical addresses are invalid. This is valid, so please don't tick it. Next, let's see C. C has segment number 6. Segment number 6 does not exist in the segment table itself. Hence, this address is invalid. So, tick that answer. Next, what is 41950? Segment 4 exists. The length itself is 96. So, an offset of 1950 makes no sense at all. So, this is also invalid. Hence, the right answers are A, C and D. Because addresses A, C and D are invalid logical addresses. Right? Very simple. You have to be careful with MSQs. Go through each of the options, read the question carefully and avoid silly mistakes. You'll get full marks on it. And this is, again, MSQs is one place, if you're careful, you can have an advantage. Because we believe that lots of people will make silly mistakes. This is literally a trap for people whose conceptual clarity is not right and who make silly mistakes. So if you are careful with it, that's your advantage in the examination. Cool. Let's go to the fourth problem now. Simple fill in the blanks problem. So Rajesh is asking about multi-level paging. We have questions. Just be patient. We have a couple of questions about multi-level paging. Just wait for it. We have not yet finished all the questions. We have some questions. Don't worry. Again, this is just the first iteration of operating systems. We have multiple iterations. We hope to do at least, hopefully, if everything works well, we'll do 3 iterations before the examination. So we'll try to cover everything. Okay, let's answer this. Again, this is a fairly simple question, but you have to be careful with it. That's all. Because there's a lot of base 2, base 10, all of that stuff. So you have to be careful not to mess those things up. Yeah, Keshav says, please notify us when you upload new syllabus for 2021. Sure. As and when we upload any new chapter or new content, we'll keep sending you emails of all the updates that have been made. We'll surely do that. And any new syllabus, we'll call it out clearly so that if you have already completed that subject, you can visit those videos only. We'll surely send you those videos or those chapters or those modules. Okay, I'm seeing a few answers being put out by people. Again, please be careful. This is very easy to make silly mistakes on. Okay, I see multiple answers. Again, some of you got it incorrect from the chat window, so please be careful. The most common mistake here is the conversion from base 2 to base 10, and again thinking in terms of base 2 and base 10. So think about it a little carefully. Okay, some of you have answered this question. It's not very hard. It's actually fairly simple, but prone to errors. The right answer is 912. Let me explain how we arrive at it. First and foremost, the logical address is 400 in base 10. First, let's convert 400 in base 2, because all your page numbers, frame numbers, everything is in base 2, right? All these are binary. So what is 400? 400 is 256 plus 128 plus 16. So when you start writing 400 in base 2, you will get 11001 00. This is what it does. 2 power 0, 1, 2, 3, 4. 2 power 4 is 16. 5, 6, 7, 128, 8, 256. Yeah. So this is what 400 is in base 2. But remember that the logical address is 12 bits. How many bits do we have? 4, 4 plus 4, 8 plus 1, 9. It should be 12 bits. So let's add 3 more bits here, because it says clearly that it's 12 bits, right? So this is what 400 is in base 2, first and foremost. From here, it's very clearly visible that the page number is only the first 4 bits. And what is the page number here? 0001. So 0001 corresponds to a frame number of 0011, right? So this is your logical address. The question says the corresponding physical addresses. Let's start filling in the physical address. So 0001 will be replaced by 0011, right? The offset will stay the same. The offset is 1001 0000. Look at this. Only the first 4 bits have been changed. Rest everything. The first 4 bits have been changed. The page number got replaced by frame number, right? Except that this whole thing has been, this offset is copied as is. Right? This is your page number replaced by frame number, offset copied as is. Now, if you see this and if you expand on it, again, if you convert this from binary to decimal, you will get 912. Very simple. That's all there is literally, right? So if you convert this from binary to this, you'll get 912, right? So again, you can do it very quickly. If you notice this bit, all of them are same. Only one additional one came. So this is nothing but 400. So to 400, you have this. This is 256. This is 512. So just add 512 to this, you get 912. Very quickly you can get the answer 912. That's it. That's all there is. It's just that the number of bits for page number and all are not explicitly listed, but by just looking at the page table, you can decide for that. Right? It's a very fairly simple problem. Okay, let's go to the fifth problem. Somebody was asking about multi-level paging, right? Yes, here comes the problem. Again, fairly simple problem. Very similar to the previous year gate questions. Very similar in nature. This is fairly simple. If you know the concept of multi-level paging and if you can think about it, you can answer this fairly quickly. Okay, I see that people are putting in a wide spectrum of answers, 2, 3, 4. Anyway, just think through it. It's a simple problem. If you think through it, it's fairly simple. Again, just think about it. It's a fairly simple. If you know multi-level page tables, this is actually straightforward. Folks, we may not be able to answer all the general questions in this live session. So please feel free to email us in case we miss out any question. Please feel free to do that. Okay, many of you got it right, which is good. So the answer is 3. It's straightforward. Look at this. Your logical address is 32-bit. Right? So your logical address is 32-bit. This whole thing is 32 bits. Okay. So now what does it say? And 1 kilobyte pages. Each page size, right? Page size is 1 KB. What is 1 KB? Is 2 power 10 bytes, which means your page offset will be 10 bits. Your offset is going to be 10 bits, which means you have 22 bits for the page number. If you just do one level paging, right? Again, you can have level 1, level 2, level 3, all sorts of pagings here. So you have 10 bits for the offset. You have 22 bits for the page number. Now look at this. If you have 22 bits for the page number, what are the total number of pages that are possible? Pages that are possible are 2 power 22. Those are the total number of pages. How does your page table look like? Your page table, right? Look at this. This is your page table. Each entry in the page table, it also says each entry takes 4 bytes. 4 bytes is nothing but 2 power 2 bytes. So if each entry takes 2 power 2 bytes and you can have a total of 2 power 22 pages, what is the size? What is the imagine if you have one level paging, right? Imagine if you have one level, just single level paging, right? What will be the size of this page table? The size of the page table is 2 power 22 into 2 bytes, which is 2 power 24 bytes. But this 2 power 24 bytes does not fit into one page, or to be precise, it doesn't fit into one frame. The page size equals to the frame size, right? It doesn't fit into one frame because one frame can only take 2 power 10 bytes. So one level paging will not work, right? Obviously. Now again, you can work step by step and quickly realize that if you start doing if you start doing 2 level paging, look at this. If you do 2 level paging, what happens? Right? Let's see. If you do 2 level paging quickly, look at this. You have 2 power 24 bytes in the first level paging. So you can say 2 power 24. The size of each page is 2 power 10 and the size of each entry is 2 squared. So this will say if you are using 2-level paging, you need the frame size to be greater than equal to 2 power 16 bytes. But the frame size equals to page size, which is 2 power 10. So 2-level paging also won't work. Again, we have explained how to arrive at these numbers and how to arrive at these equations from first principles in the course videos. I'm just doing it in an examination format to be fast, right? Let's go to 3-level paging now. If you're doing 3-level paging, you have 2 power 16 bytes here. So you can quickly do it and say 2 power 16 by, what is the size of each page? 2 power 10 and 2 power 2 bytes. So what will this be? This is 2 power 18 by 2 power 10. This is 2 power 8. 2 power 8 is less than 2 power 10, which means this can fit. If you're using 3-level page, if you're using a 3-level paging, this will fit into one frame, right? So how will this whole thing look like? Again, this is one way of arriving at it. Other thing that you can quickly do is, look at this. This has 22 bits, right? In one page table, look at this. The size of the frame is 2 power 10 bytes. Each entry is 2 square. So 2 power 10 by 2 square, which is 2 power 8. So you can only have 2 power 8 entries in any frame, right? That's the maximum number you can have. So if you look at your logical address, 10 bits are taken by offset. The maximum number of entries you can have in each frame is 2 power 10 by 2 power 2, which is 2 power 8. Why is this 2 power 2? Because each page entry requires 4 bytes. So you can have 8 bytes here, then 8 bits, 8 bits and 16 bits. That's what will give you 22, right? Right? This is also a quick way. Instead of going through this cumbersome way, another way of thinking about it is, see what is your page size. Your page size is 2 power 10 bytes. Each entry is 2 squared bytes. So which means how many entries can you have in one frame? You can have at most 2 power 8 entries. So let's create 8 bits here. The total here has to be 22 bits, right? So 8 bits for the 3rd level paging, 8 bits for the 2nd level paging, 6 bits for the 1st level paging, right? So you need 3 levels of paging to solve this problem. Again, a slightly more variation to this could be, what are the number of bits for 1st level paging, 2nd level paging and 3rd level paging? That's a slightly more involved question. Instead of asking just number of levels, they could ask how many bits are there for 1st level paging, 2nd level paging and 3rd level paging. Then the answer will be 688. Very simple question. If you know how multi-level paging works, this is more or less straightforward. Okay, so let's go to the 6th question now. Oh, this is a, 1 second, let me move this slightly to the right. This is an MSQ. Please mind that this is an MSQ and it's an easy question. Again, this is an MSQ, so please be careful. It's actually an easy question. Again, the question is lengthy, but it is simple. Again, please read the question carefully. It's very prone to silly mistakes. We'll be creating more interesting MSQs as we go forward. We have already started creating some of them, but I mean, we have some nice ideas and we got some inspiration from the JAM exam question paper also. Okay, some of you have started putting in the answers. Good, good, good. The question is lengthy. It's simple actually. If you know about the bitmap bitmaps that are used to handle disk partitions, it's actually fairly simple. Or not disk partitions, disk blocks. I'm sorry. Okay, most of you got it right. So let's go into if you know the concept, again, most of these concepts in operating system, at least for the last topics, if you know the concept, you can trivially answer it. Okay, so this is the pattern that we have initially. So let's go step by step. It says the first bit is the root partition. So we will not touch it because it says clearly, right? 1 represents the first block used by the root directory, right? By the root directory itself. So let's not touch 1. Okay, it's already taken up by the root directory in Linux. Okay, so the system always searches for free blocks. Okay, that's all cool. Let's see each of the options. File B is written using 4 blocks. Okay, so when you have, using 5 blocks, not 4 blocks, I'm sorry. So which are the free ones? These are the free ones, right? Zeros are free, 1 means occupied. So again, it goes from leftmost bit to the rightmost bit. So after you do this, 1, 1, 1, 1, 1. These 5 bits will be occupied by B, right? So this is being occupied by B. This is being occupied by A right now, right? This is being occupied by A, right? 6 blocks, okay? And each block corresponds to 1 bit here. So file B is written, file A is deleted. When file A is deleted, what happens? This becomes 0, 0, 0, 0, 0, 0. So file A is no more here. It got deleted. So they all get freed up, right? So this is anyway root. So let's not touch that. So A got deleted. Then C is written using 8 blocks. Remember the 6 blocks here are free, right? 6 blocks here are free. So these 6 blocks will get used up first. This is root. So C will use this C will use this 6 blocks. It will also use 2 blocks from here, right? So there is some splitting happening. Right? This is also called as, you have some part of C here, you have some part of C here. That's perfectly valid. It happens a lot when data is stored in disk blocks. Okay. Then B is deleted. When B gets deleted, what happens? You get 0, 0, 0, 0, 0. So let me just erase this. This is what you are left with now. Right? Now let's see. What are the options given to us? Let's see all the options. There can only be one correct option, right? Which means, and the question says is not. Which means 3 options have to be incorrect. Obviously, there is only one possible correct answer. Okay, it could so happen that all the 4 are incorrect. So let's see if this exists anywhere. So 4 ones. Okay, you have 4 ones here, you have 4 ones here. Then 1, 1, 1, 0. It could be this or this. Then all zeros. So it can't be this. So this is the right. So this is the final string of the bitmap. This is a final bitmap string. Rest everything are not. So the question says which of them is not. So A, B, and C is the right answer. That's it. If you're careful with it, if you know how the bitmap pattern for disk organization works, it's fairly straightforward. It's an easy MSQ. Okay, so let's go to the next problem. Again, this is also interesting but very common gate pattern. Very common gate pattern question. There is a small trick here. I'll tell you when I end up solving it. There is a small trick to solve these types of problems about inodes fast. I think I discussed that in the solved problems of the course videos also. This is not an MSQ. There is only one answer here. Okay, some of you are putting in the answers. Let's wait for others also, then I'll go into the solution, detailed explanation of the solution. We have 4 more questions, we have 20 minutes, we should be able to finish them. Okay folks, so let's go into the solution of it. Most of you got it right, D is the right answer. So look at this, what is our block size? Our block size is 1 kilobytes, which is 2 power 10 bytes. And everything is 4 byte disk addresses, right? 4 bytes is 32 bits. So disk addresses are 32 bits. What is the maximum file size approximately, right? So they're not looking for the exact number. If the inode contains 10 direct block entries, 1 single indirect, right? 1 single indirect. So 1 single indirect. Then you have 1 double indirect, right? 1 double indirect and 1 triple indirect. Okay, 1 triple indirect. So let me solve the question thoroughly, then I'll tell you a shortcut. Okay. So first and foremost, note that it also says each block is 1 kilobytes, right? So you have 10 direct, which means you have 10 kilobytes of space that can be assigned to that, because each inode corresponds to a file. A file can be, so that's what it asks, right? The question says maximum file size. Yes, for every file you have an inode. So 10 kilobytes using direct addressing. Using indirect addressing, how many do you have? That's an interesting question. Look at this. So you have one block here, which is of size 1 kilobyte, which is 2 power 10 bytes. And it says each address is 4 bytes. Each address is 4 bytes. So how many addresses can you have here? You can have 2 power 10 by 4, which is 2 power 8 addresses you can have. And in single indirect, it's like a pointer. Look at this. It's like a pointer. This will point to this and this will point to the blocks. So you can have 2 power 8 blocks, which means you can have 2 power 8, which is 256 blocks. Each block is 1 kilobyte. So 256 kilobytes, or in other words, 2 power 8 kilobytes. Double pointer is like a, double indirect entries is like double pointers. So in the first level, you can have 2 power 8. In the second layer, you'll have 2 power 8. So you'll have total of 2 power 16 blocks, and each block is 1 kilobyte. So you have 2 power 16 kilobytes. In the triple, what do you have? First level, you will have 2 power 8. Second level, you will have 2 power 8. Third level, you will have 2 power 8 kilobytes. Now, one thing that you can notice here is this is just 10 kilobytes. This is 256 kilobytes. This is 2 power 16 kilobytes. What is 2 power 16 kilobytes? Is 2 power 6 into 2 power 10 kilobytes, which is 2 power 6 is 64 megabytes. Now, what about this? This is 2 power 24 kilobytes. 2 power 24. Kilo is 2 power 10. So plus 10. So you have 2 power 34 bytes. What is 2 power 34? 2 power 34 is 2 power 4 gigabytes, which is 16 gigabytes. So whenever you have inodes, the triple pointers, if you have a structure like this, the triple pointer will matter most. Look at this. The triple pointer can point to 16 GB of space. The double pointer can only point to 64 MB. The single pointer only to 256 KB. Direct pointers only to 10 KB. And the question says clearly that you have to compute approximately. So when you have something like this, you can simply ignore direct, indirect. Look at the largest. The largest possible pointing that you can have is the triple indirect block entries. The triple entries or the triple pointers are the largest. So if you can figure out this 2 power 8, this is all that matters, and 16 GB is the right answer. So as a shortcut, you don't have to compute this, you don't have to compute this, you don't have to compute this. Just compute whenever a similar problem is asked, just look at the largest possible here. Here you have a triple pointer like structure, right? Again, that's how I remember these concepts. I remember all of page tables, all of these inode structures. I remember them as I connect them to basic data structures and programming. That's how I easily remember some of these concepts. Actually, if you see the source code for inodes in Linux, they're all implemented using pointers. Okay. Again, I think of them as triple pointers only in my head. Easier to solve these problems. Okay, cool. So let's go. Let's go to the 8th question now. Okay, this is an easy question. Fairly easy question. But again, please understand that this is very easy to make a mistake on. Please be very, very careful here. This is an easy question, but also very easy to make a mistake on. Read the question carefully. I see people putting in the answers. Please be careful. Typically questions like these are 1 mark questions, but very likely to make mistakes on. I see a lot of people, I see a couple of people putting in the answers, but again, committing mistakes. Please read the question very carefully. Again, guys, I think all of you are putting in the answers, but not reading the question carefully. Please. Please read the question carefully. I was expecting that people will make a mistake in this question. Yeah, as our mentors are saying, some of you are in a hurry to answer. Most of you got it incorrect. So please read the question carefully. As I told you at the very outset, for this question, it is a tricky question. It's a when we see the answer, it will feel very simple, but very easy to make a mistake on. Okay. Very few amongst you got it right. Most of you got it wrong. Okay, anyway, let me answer it because most of you are getting it incorrectly. Probably you're missing something in the question. So let's read the question. Assume the style of inode storage where the inode is stored at the first block of a file, right? It's given that the inode for the root directory is in the memory. So this is your root directory. Its inode is already in the RAM, right? Its inode is already there in the RAM. It's already in memory. Memory here means main memory, but nothing else along the path is in memory. At the end of the day, if you want to read anything, you have to get it to memory, right? That's obvious. Now also assume that each directory fits into one disk block. Very good. And it takes one disk operation to retrieve the inode, one more operation for the directory contents, right? Now let's see. Okay, this is very important. I'm just underlining everything that is important. So inode, okay, so given that the inode for the root directory is already in the memory, this is also important. This is your root directory. The number of disk operations that are needed to fetch the inode for the file A, B, C, D, E. So E here is the file. A, B, C, D is the absolute directory path and E is the file name. That is clearly given. So for this, look at this. For the root, you already have the inode in memory. So you don't have to, again, the two operations, retrieve the inode and then retrieve the directory contents. For the root, you don't have to retrieve the inode itself because it's already there in the memory. So for the root, you only have one operation, which is fetch the contents first. Once you see, the inode is already there. So first you fetch the contents. Once you have the contents, now you want to go to a folder A, right? First you fetch the contents, right? Then to go to A, there are again, because this is a directory now. A is in another directory, right? This requires two operations. Why does it require two operations? One, again, it's written clearly here. One disk operation to retrieve the inode corresponding to this. one disk operation to get the contents of A, right? Similarly, next subfolder is B. Again, B also will involve two disk operations, one to retrieve the inode, another to list the directory contents, right? Then you have C also 2, D also 2. Finally, you have E is a file, right? So it says, read the question carefully, the number of disk operations that are needed to fetch the inode for the file E. We are not looking to get the contents of file E. We only want to fetch the inode for this. So fetching the inode for E is one operation. We are not going to go into directory contents because E itself is a file and we don't care about it in the question. So what are the total number of operations? 1 plus 2 plus 2 plus 2 plus 2 plus 1, which is equals to 10. Again, this question is lengthy and tricky, but it's easy. Very, very easy to make silly mistakes on, right? So you have to read the question carefully. That's all is the trick here. If you read the question carefully, understand what is being said, the right answer here is 10. Not, I think only 1 or 2 of you got it right. Okay, so that's what this is. It's a tricky problem, but an easy one. It's just simply counting 6 numbers. That's it. Okay, let's go to the next question now. This is a standard gate type question. This is about disk access times and things like that. Very standard question. Again, if you know how to compute the standard disk access time, this is a straightforward problem. It's a very common gate type problem which is asked for 2 marks typically. Again, just apply the standard process that you have learned in our course videos or in standard textbooks or wherever you're preparing for GATE. This is a straightforward problem. But also prone to errors. Again, please don't miss any of the parts of the disk access time. There are multiple components of the disk access time. Please don't miss any one of them. If you miss it, you'll get an incorrect answer here. Actually, questions like these are often asked as fill in the blanks because people who set the GATE question paper know that candidates will miss one or other thing or make some mistake in the calculation of one component of the disk access time. That's why they give questions like these as typically fill in the blanks. Of course, no negative marking, but still, you have to be careful. See, I'm already seeing in the chat window 3 completely different answers. 3 completely different answers. Oh, 4 completely different answers now. Wow. Again, I'm seeing the chat window on a different computer, actually on my phone. 5 different answers, guys. 24.2, 18.6, 21.4, 64.9, because we say rounded to the 1 decimal digit, 23.9, 24.1. Wow, it's all around the place. Wow. I hope I didn't mess up the numerical computation. Anyway, we'll solve it together. Oh, such a huge variance in answers. Anyway, take some more time. Those who are solving it, please solve it. I'll surely go through the answer in detail. We might overshoot this session by a few minutes, but that's okay. Let's solve it thoroughly. We always try to wrap up a session in 60 minutes, but very often it gets overshot because we try to answer some miscellaneous questions also. Okay. Somebody says he wants to skip this question to avoid negative marks. There is no negative mark. This is a fill in the blank question, dude. This is a fill in the blank type of question. There is no negative marking here. Again, if you don't know this concept, best to skip it and not waste time on this, because there is some numerical computation that you have to do carefully. Okay, so let's try to answer this, right? So you have disk access time. Disk access time is seek time, right? What is our seek time? Let me write the whole expression. Plus rotational latency, right? So you have to first seek, then rotate, then you have transfer time, right? Then what do you have? You have controller time, right? The actual hardware controller. Sometimes you have something called as queuing delay, right? Sometimes you have something called as queuing delay. So let's see what all are there for this problem. So let's start filling it up. 12 milliseconds seek time. So this is 12. Let's compute everything in milliseconds. Okay. There is rotational latency. Of course, you are given the RPM. We'll compute it. We'll compute that in a couple of minutes. You have transfer time also, because you have 4 Mbps, 4 megabytes per second to be precise. The controller overhead is 1 millisecond. So this is 1 millisecond. And it says the initial disk is idle, which means there is no queuing delay. Queuing delay happens if the disk is not currently idle and your requests for some sector, right? Your requests for getting some data from the disk is queued into something. There is no queuing delay here, right? Again, this is often not even considered. As far as gate previous questions are concerned, you don't have this queuing delay type of questions much. Okay. Now let's look at rotational latency. Let's go step by step. What does it say? 5,400 revolutions per minute in 60 seconds. So which means in 1 second, how many rotations? 90 rotations per second, right? Again, how do you compute rotational latency? Rotational latency is taken as the average rotational latency. The average latency is taken as half of the maximum latency. That's what it's taken as, right? Again, you can think of it like the expected or the average latency. So this is half is 0.5. What is the maximum latency? Look at this, one rotation. Look at this, 90 rotations take 1 second, which means one rotation takes 1 by 90 seconds, right? So the rotational latency or the average, see in this case, you don't know how much you have to rotate. So you often in practice, as we have discussed in the course videos also, you take the expected or the average rotational latency. It is 0.5 by 90, right? So what is 0.5 by 90? It is roughly it's 5.5 milliseconds. Okay, so this turns out to be 1 second. This is seconds, right? 1 second. So this is seconds. So let's convert everything into milliseconds because the question says milliseconds, right? So this is 500 milliseconds, right? 0.5 seconds is 500 milliseconds by 90. So these two get cancelled out. So it's 5.5 milliseconds. Okay, I want to avoid mistakes. Okay, so rotational latency is 5.5 milliseconds. What about transfer time? Again, this is also fairly simple to compute. Look at this. It says the transfer rate is 4 megabytes in 1 second. That's what it says. And look at this. You have 512 bytes per sector. You copy a sector, right? So how much time does it take for 512 bytes now? 512 bytes is 512 by 4 mega. 4 mega is 2 power 2 into 2 power 20. And this is 2 power 9, right? This is 2 power 9. So if you simplify 2 power 9 by 2 power 22, you will get 1 by 2 power 13 seconds. What is 1 by 2 power 13? It is 1 by 2 power 3 into 1 by 2 power 10. 1 by 2 power 10 is roughly 1000. 2 power 10 is roughly close to 1000, right? If you think about it. So this is your millisecond, these many seconds. So 1 by 2 power 10 seconds is approximately 1 millisecond. So 1 by 8 milliseconds. Now what is 1 by 8 milliseconds? 1 by 8 milliseconds is roughly equal to 0.125 milliseconds. We only want one decimal place. So let's start counting it. 12, 5.5. Transfer time is 0.125. Then you have controller time, which is 1. So what do you have? You have 12, 17, 18. 18.625. You can ignore the 0.25. So you get 18.6. That's the answer. Right? So all that you need to know is how to compute rotational latency, how to compute transfer time. Seek time is given to you. Controller time or controller overhead is given to you. Queuing delay is anyway 0. So if you just know this formula and if you know how to compute each of these components, it's a straightforward problem, but very, very common problem to commit silly mistakes on. Right? Again, we have solved tons of problems like these in the course videos also. So if you know the concept, this is straightforward. Right? Cool. Okay, let's go to the last question. Yeah, somebody says 1 mega is roughly 10 power 6. Yes, it's roughly equal to 10 power 6. Yes, that's true. So 1 kilo is roughly equal to 10 power 3. 1 mega is roughly equal to 10 power 6. 1 giga is roughly equal to 10 power 9. So you can do these approximations in most problems. Because we are only looking at the first decimal digit, right? Cool. This is a simple, straightforward, easy problem. Yeah, our mentors have given a much more subtle answer. That in memory, it's 2 power 10. In bandwidth, it is 10 power 6. Anyway, that's a good subtle detail. Okay, here is the last question of the day. I know we have overshot by a little, but it's straightforward. Let's solve this question and then we are done. This is a standard shortest seek time type of disk scheduling. Again, there is a lot of commonality between disk scheduling and process scheduling, a lot of similarities. Again, we are intentionally giving some fill in the blanks because that will help you become better at solving the problems more thoroughly. Again, at this point, conceptual clarity is more important rather than the tricks. Gate has never been about tricks. Gate has always been about conceptual clarity and rigor. There is some little bit of computation that you have to be careful, or numerical computation that you have to be careful here, but it's a simple problem. If you know shortest seek time first based disk scheduling algorithms, this is straightforward. Just be a little careful with the numerical computation part. Okay, some of you have started putting in the answers. I see 2 different answers here. Somebody says 44.7. How come? Wow. How can the disk arm move a non-integer value? Okay, many of you got it right. The answer is 1745. Let me explain how the solution is arrived at. It's very simple. Again, what does it say? Suppose the disk drive has 5000 cylinders numbered between 0 to 4999, blah, blah, blah. It's currently serving the cylinder 143 and the previous cylinder is 125. This is just useless information. This is used to trick you and make you fall into a trap in case you don't know the concept clearly. The queue of pending requests, all of them are there. All of these requests for these cylinder numbers is already there. They're there in the pending requests. Now from the current head position, the total distance that the disk arm moves to satisfy all pending requests using shortest seek time first. So currently it's at 143. All of these requests are pending. Look at this, all these are pending, right? So that's important. All these are pending. So after 143 is served, where would it go? Shortest seek time, right? Which is closest amongst all of them. 130 is closest. So from 143 it will go to 130, and how many cylinders it would move? 13 cylinders it would move. So after it serves 130, so 130 is done. After it completes 130, which is the closest? If you observe, 86 is the closest amongst all the others. So then it will go to 86, right? So how much is the change here? 44 cylinders it moves. Then after 86 is over, what is the next closest? 913, right? So next is 913. So from 86 to 913, this is a change of 827 cylinders, right? So 913 is done. After 913, where would it go to? 948 is the next closest. So then it would go to, because we are using the shortest seek time, right? The seek time is going to be shorter because look at this. The whole cylinders are from 0 to 4999. So whichever you can move, whichever is closer, that's you can seek that faster, right? Using your current head positions. Okay. Next is 948. So what is 948 minus 913? This is 35. After 948, what is the closest now? 1022, right? 1022. So if you're using 1022 minus 948, this is 74, right? After 1022 is over, what do you have? Which is the closest? Closest is 1470, right? So you have 1470 here, which will create 448. Again, I've already computed this. That's why I'm able to write it fast. Okay, I've already computed this when I was solving this problem before the live session. I always try to solve the questions that our team sets before the live session so that I don't make silly mistakes in the live session itself. So then you get 1509, right? So then you get 1509. What is this? This is 39, right? Yeah. So 1509 is also over. Then you get 1750. So 1750 is 241. Then finally you have 1774. 1774, that is 24. Now you sum this with all of them in a calculator. You get a calculator, right, in the GATE exam. So sum all of them, you'll get 1745. That's the answer. And this is the end of the first iteration of operating systems. And I know we have overshot by close to 10 minutes. The next live sessions we will conduct on 14th, 19th and 21st of this month. And it will be computer organization and architecture. Again, any questions that we could not answer because it's a public live session, it's impossible to answer every question. Feel free to go to gate.appliedcourse.com and you can email us at gatesc@appliedcourse.com. We will try to answer as many questions as possible. Okay. See you on the coming Friday. Thank you very much. Thank you for joining this session. Bye-bye. Have a good night.